Hope you're all doing good. In this video lecture, we'll be learning about solitons. So, what is a soliton? A soliton is nothing but a special wave which is used for propagation in an optical fiber communication system. So, if you're using solitons, there are a lot of advantages. In a long haul communication system, dispersion is one of the limiting factor, and because of dispersion, the bit rate gets reduced to 9 gigabits per second. So if you are using our special waves called solitons, the dispersion can be minimized as well as the bit rate can be improved from 100 to 200 gigabits per second. So solitons are nothing but a special wave used for propagation in a communication system. So, from where we get the soliton? What exactly is a soliton? Soliton stands for solitary solutions. Okay, the solitary solutions are obtained by solving nonlinear Schrodinger equation. So, if we are modeling our optical communication system by using a nonlinear Schrodinger equation, and if we are solving that particular equation, we get solution, and that solution is known as solitary solutions, and that solitary solutions we get in the form of a special wave which can be used for the propagation in optical communication system. By using such special waves, we are limiting the dispersion and also improving our bit rate. So, what is the basic principle of working of a soliton? It is the counteraction of self-phase modulation and group velocity dispersion. We'll be explaining in detail more about self-phase modulation and group velocity dispersion in the coming slides. And another important factor regarding the soliton propagation is that the communication system, it can be used in those optical communication system where it is handling high power. The pulse energy should be sufficiently strong for the soliton propagation. And also the soliton propagation is used in the range of 1320 nanometer. In that wavelength, we are using soliton propagation. So, soliton propagation is used for high pulse energy systems and also in the range of 1320 nanometer. So the wavelength dense multiplexing systems can also be used with soliton propagation. So in wavelength difference multiplexing system, through different channels, different solitons can be propagated and that does not interfere with each other. So in soliton wave, a soliton wave is a wave that retains its shape in spite of the dispersion and the nonlinearities. How the soliton wave retains its shape because of the dispersion and nonlinearities is that because of dispersion, associated with dispersion is group velocity dispersion. Because of group velocity dispersion, there is a broadening of the pulse, and because of non-linearities also there is a broadening of pulse. So when you're combining this group velocity dispersion and this non-linearities, the non-linearities is mainly due to the Kerr effect. So these two effects nullify each other. The group velocity dispersion causes one broadening and non-linearities causes another broadening, and these two broadenings are equal and opposite in direction such that it nullifies each other, and hence the pulse is unaffected, and hence the soliton pulse is unaffected. So this is a basic principle behind which the soliton works, that is the counterpart. It works counterpart between the group velocity dispersion and the non-linearities. Okay, so a soliton pulse is a constant amplitude optical narrow high intensity optical pulse. As you can see from the figure, it is a narrow high intensity optical pulse. So as I told you, the soliton, the basic principle of working of a soliton is the counterpart operation of group velocity dispersion and the self-phase modulation. Because of the self-phase modulation, we have a non-linear effect. Non-linear effect normally known as a Kerr effect. Because of the Kerr effect, there is a change in refractive index. Because of the change in refractive index, so when a wave is propagating through that change in refractive index medium, there will be a broadening of that pulse. Okay, and because of the group velocity dispersion, as we have already learned, there is a pulse broadening. So in the first figure you can see because of group velocity dispersion, there is a pulse broadening of the pulse, and when This group velocity dispersion fiber is then subjected to cell phase modulation because of nonlinearity Kerr effect. There is a change in refractive index. Because of that, there is another broadening of pulse, but which is in opposite direction, opposite polarity of that of group velocity dispersion. Hence, that broadening is nullified, and we get the same pulse that has been propagated from the transmitter side at the receiver side. So from here it is very clear that the basic principle of operation of a soliton is the counterpart operation of group velocity dispersion as well as cell phase modulation. Now we'll see more about cell phase modulation and group velocity dispersion. As you all know, the wavelength of the red color is 650 nanometer as well as for blue is 450 nanometer. And we have an inverse relation of wavelength and frequency. So here the red has higher wavelength, that means red has lower frequency, and blue has lower wavelength, that means blue has higher frequency. So in cell phase modulation, the lower frequency components, that is the red color components, will be at the starting edge of the pulse in cell phase modulation. Similarly, the higher frequency components will be at the lagging end. Okay, so for the cell phase modulation, the low frequency components are at the starting end or the leading end, or similarly the higher frequency components are at the ending end. Okay, so in group velocity dispersion, this will be, we have to nullify the effects that are caused by cell phase modulation by group velocity dispersion. Then only our soliton wave will propagate without any distortion in the shape. So in order that we have to have a opposite, like the starting edge should be having high frequency components. Similarly, the ending should be having similarly the opposite, lower frequency components, then only the effect will be nullified. So group velocity is basically of two types: positive group velocity and negative group velocity. The positive group velocity has a polarity almost same as that of cell phase modulation, and the negative group velocity has the polarities different, opposite that of cell phase modulation. So in soliton propagation we'll be using negative GVD. Okay, so in negative group velocity dispersion, the higher frequency components will be at the starting end and the lower frequency components will be at the ending end. Because of that, there is a nullification happening, and there will be a cancellation of dispersion, and finally the soliton wave can propagate. So you can see in the figure that is explaining the cell phase modulation. The cell phase modulation is a non-linear effect, and because of non-linear effect, commonly known as the Kerr effect. Because of this Kerr effect, there is a change in refractive index of the material. So the figure 1, you can see waveform that are having a constant frequency omega naught. But in the second figure, as you can see, when it is passing through a optical Kerr medium, that is that medium which has non-linearity. Because of that, there is a change in refractive index material, sorry, change in refractive index of the material, as the light waves that are propagating through this optical Kerr medium will be at different instance, they will be having different refractive index, and they will be at the different instant, they will be having different like the shapes at the different instant of time will be different, the frequencies will be different. And in self modulation, as we have already learned, the starting edge of the pulse will be having the lower frequency components, and the leading ending edge will be having the higher frequency components. So from the figure it is very clear that the starting edge has the lower frequency components, and the ending part has the higher frequency components. So this is the effect of self phase modulation. So you can see from the figure, the two effects introduce a change in frequency in two different opposite direction. So that that Kerr effect, because of Kerr effect or cell phase modulation, the frequency, the lower frequency components are in the starting edge, the higher frequency components and the ending edge. Similarly, the opposite is the case for group velocity dispersion. The higher frequency components, as you can see from the figure, the higher frequency components at the starting end, and the low frequency components are at the ending end. So when these are two combined, the two effects will be nullified, and a pulse will be a balanced pulse that can propagate without the broadening, and the dispersion is obtained. Okay, this is the basic principle of a soliton. So talking more about cell phase modulation, it is a nonlinear effect, also known as a Kerr effect. It occurs in high power systems. As we have already said, the solitons normally occur in high power systems, and these cell phase modulation are most commonly in single mode fibers. Because of cell phase modulation or the nonlinear effect or the Kerr effect, because of that there is a change in refractive index of the fiber. When there is a change in refractive index of a fiber, when an optical pulse is being coupled through an optical fiber, because of the change in refractive index, there will be that introduces phase fluctuations in that propagating wave, which can result in chirping effect. Chirping effect, as we have already learned, the change in this shape of the pulse. There can be phase fluctuations and also frequency fluctuations because of this change in refractive index of the material, because of the non-linear Kerr effect, which can result in chirping effect. So, as already discussed, the group velocity dispersion is basically of two types: positive group velocity dispersion and negative group velocity dispersion. Now we see how a medium with positive group velocity dispersion acts. As I already said, the positive GVD is almost same to that of cell phase modulation. The leading part of the pulse has lower frequency components and the trailing part has a higher frequency components. So since the low frequency part, the speed is high than the higher frequency part, there can be a lag because the starting part the speed is very high and the ending part the speed is low. So because of that, the change in speed left from high to low, there can be a delay at the trailing edge. This can lead to the distortion in shape of the pulse. As you can see from the figure, there is a distortion in the shape of the pulse as the time progresses. And in negative GVD, as I already told, it always acts and counteracts with the cell phase modulation. So here the leading part has higher frequency components and the trailing part has lower frequency components. Since the higher frequency part is with the starting edge, there is no delay, there is no delay part, hence there is no distortion in the shape of the pulse. As you can see from the figure, all the pulses are in same size and same shape. So concluding, cell phase modulation in counteracting with negative GVD is used for soliton propagation.